So for today, basically all I have planned is that we're just going to continue kind of reviewing through some of the material, right? After we looked at, yesterday, after we looked at the hydrolysis of esters reactions, we just started through some review, and we went through, reminded ourselves about all the different functional groups and made sure that we can identify those in structural drawings, and we did some naming, okay? So I thought today what we would do is spend some time just focusing on the different reactions that we've learned, right? So we can make sure when we see a reaction, we know what to focus on, what to look at, and then hopefully know the outcome as well, all right? And then I think tomorrow we'll kind of talk about some carbohydrates, review a little bit about those. Monday, maybe we'll look at the old exam. So, we got like forever reviewing here. I don't know how we went so fast, or how the last time I taught this I had the same schedule and I don't remember this situation. Okay, so don't forget about the homework, and the quiz is still going on for this week, due on Monday, right? Our exam is on Wednesday. I'm still going to have to work out the room for our exam review session is on Monday, and then Jared's, out of the kindness of his heart, is having another office hour on Tuesday just to pick up any loose ends right at the last minute. Okay? All right, so let's just go with blank slides. All right, so let's just think about some review. I don't have anything drawn out here, but we're just going to work our way through. Okay, so the main thing we want to do today is review on reactions. Okay, so the reactions that we've learned have basically been grouped into functional groups, right? So we had our functional groups, we had the chapter on alcohols are the main things that reacted in that chapter, and then aldehydes and ketones, carboxylic acids, and esters, right? So let's maybe just start with some alcohols first, and we'll just try to think of what kinds of reactions we might be able to do. Okay, so here's just an alcohol. So what kind of alcohol is this? Primary, secondary, or tertiary? Secondary. Okay, you guys are getting so quick at that now. So what kind of reactions, what can we do to a secondary alcohol? Anybody remember? Oxidation. Excellent. So we could write out, if we were going to do an oxidation, we might just see something like this, right? And if we have this secondary alcohol, what's it going to be oxidized to? What happens in an oxidation reaction? It loses hydrogens, right? It's going to lose two, right? So it's going to lose the hydrogen on the oxygen, right? Where's the other hydrogen going to come from? From where the oxygen is attached. All right, so we're going to lose those two hydrogens. And what are we going to form in the process? No, not water. We're only losing hydrogens this time, not hydrogens and the oxygen. So the oxygen is staying put. Not an acid. Not a base. A ketone. Ding, ding, ding. Dang, if this was a quiz show, you guys would all be losing money. Okay. We're going to lose those two hydrogens, and we're going to add a double bond, right? And we're going to form a ketone. All right? What else could we do to this alcohol? What if you treated this with some acid and we heated it up, you know, maybe 180 degrees or something, not that the temperature is so important, what can happen? Dehydration. I heard somebody say that. Nice. Woo! 1 point for row 4. Yeah. All right. So in a dehydration, what takes place? What do we lose? Hydrogen. Well, not only hydrogen, water, right? Just like in our bodies, we get dehydrated, we lose water, right? So when we lose a water molecule, we're going to lose the OH, and we're going to lose an H on the adjacent carbon, away from where the oxygen is attached. Here, let's write it out again here. So we'll curve this arrow down here. Let's just do the same one. So in this case, we're going to lose an OH, and we're going to lose an H on either that position, right, or this position over here. All right, so remember, this side would have 3 hydrogens. Let's just draw all these hydrogens. Okay, so sometimes we think about this in terms, if we want to remember the relative positions, we call the position that's directly attached to a functional group, so directly attached to the oxygen, as the alpha position. All right, so this would be alpha. The next positions out from that are the beta positions. Okay, so this has a beta over here and a beta over here. As long as there's a proton, a hydrogen on the beta position, then the dehydration can form a double bond going in that direction. Okay? So we have 2 possibilities. Both of the beta positions have hydrogens. Okay? So the double bond can form to either side. So our 2 possibilities are having a double bond go this way, right? And if we count these out, we could just make sure we've got, you know, we got 4 carbons. Here, let's do it with this. We've got 1, 2, 3, 4. So in one case, the double bond is forming in the middle of that 4-carbon piece. The other one is going to be forming to the end. Okay, so we could have this. We could say or form a double bond over this way. All right? So do you remember, do we get these in equal amounts, or is there one that gets formed more than the other? Which one? Yeah, the one with the most carbons attached. Okay? So this one would be the major product. Okay, so what they say is that we lose the H from the carbon with fewer H's. The beta carbon with fewer H's. This was called the Zaitsev's rule. Zaitsev's rule. Okay? The real reason is, it turns out, and they don't go into this book, is that double bonds are more stable when they have more carbons attached. Okay? And so that's kind of the bottom line. So let's just think out another one. Let's say if we had a molecule like this. Let's put it in a cyclohexane ring. We got a CH3 and an OH like this. And we treated this one with H+ and heat. What would we get? Okay, so we have to, if we see this, we have to say, oh, there's an alcohol. I know that the reactions I can do in alcohols is oxidation and dehydrations, but with H+, that's the dehydration. Okay, so then what do we have to look at in the molecule to see if a dehydration can take place here? the beta carbons. We look to see if there's hydrogens on the beta carbons, right? So do we have beta carbons with hydrogens? Yeah, right? We have, this one has 2 hydrogens. This one has 2 hydrogens. And this is a CH3 over here that has 3 hydrogens. All right, so we actually have 3 beta carbons, all have hydrogens, right? So let's draw out all the possible products, okay? And then we'll try to figure out if one would be formed more than another, okay? So, if we dehydrate up to this position on top, the CH3 group, right, we'd lose the OH and an H up there, and we'd form a double bond going in that direction. Right? So we'd form a double bond out this way, and this would be a CH2 group out here. All right, so that's one possibility. If we form the double bond to the left side, over here, right, we lose one of these protons and the OH, we'd form the double bond this way. We could form this product. And the other possibility is that we lose one of these protons on the other side, right? And we'd form the double bond over this way, okay? So what do you think about these compounds? Any comments about them? Are they all unique? One of them is, right? So what if I say there's 2 of them that are the same? Which 2 would it be? The bottom 2, exactly right. You guys knew that. These 2 are the same, right? Because we could just take one of them and we could just flip it right over and lay it right on top of the other one. So those 2 are identical, all right? So we have 2 products, 2 possible products. Out of those 2, which one do you think would be formed in a greater amount? Well, we have 2 products. This is one. This is one possible product. This is the other possible product. Which one would we form more, 1 or 2? How many people think number 1? How many people think number 2? So what did we say? What's the determining factor?
It bonds with the one that has the fewer amount of hydrogen.
The fewer amount of hydrogens, right? So which one is that? 1 or 2?
1.
It's 1, right? So we're generating the double bond that has the most carbons attached by removing the hydrogen on the carbon that has fewer hydrogens. All right? So this one would be the major product. Okay? Because the more highly substituted, when I say more highly substituted, I mean it has more carbons attached. Okay? That one's more stable. Okay? All right, let's slide. So what if we took, let's do that same molecule. What if we took this one again and we oxidized that? What would we get? Well, we could lose one H. There's an H here, but in an oxidation, how many H's do we need to lose? 2, right? Is there another one to lose?
No.
Right? Where would we want to lose it? From where it's attached. Right here, right? Is there an H on that carbon? No. So what's going to happen? Nothing. No reaction. Because it's a tertiary alcohol. Tertiary alcohols cannot be further oxidized.
And you get there, and then what's that process?
No, not to get here. I'm not quite sure what you're thinking of. Let's start with something like this. What if we oxidize this one? What happens? Right, it can react first. What does it give when it reacts the first time? Double bond O with an H. What functional group is this? Aldehyde. Right, and it was right that this can then oxidize again. What does it give after it oxidizes again? No, and alcohol is where we came from, right? Carboxylic acid. Okay. We had another way, actually starting at the aldehyde to go to the carboxylic acid, okay, that used specific chemicals, reagents to use. And this one used 2 silver ions. All right, you guys remember that? What was unique about this reaction? How can we tell it takes place if we mix it up in a test tube?
It turns red.
Silver, right? We're using silver. It makes a mirror in the... Close. There's another one like that, right? Okay, this would give us plus, let's draw it down here, plus silver, and this would be a mirror. Okay, this is called the Tollens reaction. Okay, yeah, question?
This might be stupid, but how come you don't take that hydrogen from the top of the aldehyde and the hydrogen from the carbon left that so the double bonds?
Right, okay, so the question is, why doesn't this get this oxidized by removing these two hydrogens, right? Okay. It turns out that this one especially is hard to remove because it's bound directly to a, well, it's just like an alkyl group. It doesn't really have any functionality to it. And this one on the oxygen ends up being the easier one. That, you know, the way we draw it here, it doesn't really show the process that's taking place. A lot of these reactions would go through an intermediate, so you'd have some water in here. It's kind of like the acetal and the hemiacetal reaction. So we form what's called a hydrate. Okay, and from here, then we can see that if we lose an H here and an H here and form a double bond, we go right to the carboxylic acid. Okay, so if we remove those, then we go down this way. So by removing these two, that's really more similar to the process of, you know, like on this one. We move a H here and an H here, and we form this double bond. Right up here, we move this H, and we form a double bond right here. On the other OH? Okay, so the question there was why didn't we remove this one over here? These two would be equivalent. Okay, so if we move this, I just arbitrarily picked one. So if we remove this, we'd form the double bond here. If we move the other one, we'd form the double bond here, but those are both carboxylic acids. Okay, so it doesn't matter which one. So good question. Yeah, question.
Are you able to form a double bond in O if there's already 3 bonds?
Only, so the question is if there's already, well, we can, we can only, well, we can have 4 bonds. So you mean,
Because if you form a double bond by taking out that, oh, I guess because you're taking out that top H2, never mind.
yeah. So that's kind of why, like this first example up here, where's this example up here, right? We want to remove this H, but we'd want to remove another H from down here, but there is no H there. So that's why it can't be oxidized. Okay? Any other questions? Okay, so that's the oxidation and the dehydration. All right? And so we can also think about this, and we talked about this in terms of this carboxylic acid, right? We can form this carboxylic acid right here. So this isn't only, we don't only have to think about this as a reaction of a primary alcohol or an aldehyde, but it's also, we can think about it as a way to form a carboxylic acid, right, in terms of the product rather than only in terms of the reactants. Okay? Yeah.
Can tertiary alcohols dehydrate, cause dehydration?
Yes, absolutely. And in fact, on the previous examples, right, so I did the example just a minute ago. That was that same one, right? This one. And we dehydrated that, H plus, and here, this is another symbol for heat. And we said, a mixture perhaps of this one
Oh, right.
plus this, right? And that this was the major one. Yep, so that was a tertiary one. Okay? All right, so we did primary, secondary alcohols, go to ketones, right? So what if we have something like, okay, here's an aldehyde, right? And we're going to react that with an alcohol with some acid. Okay? So what can happen if we react an aldehyde with an alcohol? No, not really. This one's related to we learned this first and then we applied it to the sugar chemistry. The double bond does go away. What kind of a functional group do we end up with? Okay, so remember the alcohol can react. We get an OH. And what else would be attached here? An O with this ether attached. Okay, so we could imagine the way that this happens is this H and this O are going to actually be this H and this O. Okay, so the oxygen, this oxygen reacts with this carbonyl carbon, and then the double bond reacts with the proton. Okay, it becomes protonated. Anybody remember what this kind of functional group is called? The hemiacetal. Right? So how do we recognize a hemiacetal? It has an OH, and what else? And an ether. Okay, it has an alcohol and an ether. Okay, so what if this one reacts with another alcohol? Let's use the same alcohol with H+. It forms an acetal, right? So how is the acetal different from the hemiacetal? Structurally. Structurally more stable? Yeah, but how does the structure differ? Oh, yeah. Does it still have the OH over here?
You got rid of.
We got rid of that OH. And what do we replace it with? An oxygen double bond? Not, if I put a, no, an ether, right? So an ether is an oxygen with 2 carbons on it, so I'm going to put the same thing over here. Right, so that OH gets replaced by the ether, and so what is this called? An acetal. Right, an acetal has 2 ethers.
What was that whole thing you said? Was that another hydration, or what was that? So you just, what that you did?
Magic, pure magic.
You had another alcohol.
Okay, and you mean in that second step?
Yeah, well, I'm just wondering what the reaction was from the top right to the bottom.
The top right to the bottom. Right, so that's just the conversion of this hemiacetal to an acetal. All right, and so essentially we get this, and then we give off another water molecule. Okay, so what's going to happen is when we add the alcohol here, this H and this OH, is going to be a water molecule that comes off. And the oxygen of the alcohol replaces the oxygen of that, the oxygen of this alcohol replaces this oxygen up here. Okay? Here, let me draw it out in a different way. I'll show you a different one. So let's do it with a ketone like this. Okay? And so this ketone is going to, if it reacts with 2 alcohols, it can form the acetal. Okay? So I'm going to draw these alcohols like this. I'll just do CH3s now. And I'll draw this H like this. Okay? And so essentially what happens here is that we generate a water molecule right here. Okay? And this oxygen gets attached to there, and this oxygen gets attached to there. Okay? So in this process, we end up with this OCH3 and OCH3. Okay, plus this oxygen here. We'll have this oxygen, and it has 2 H's on it now. Okay? Unfortunately, some of these things, if you took a more in-depth organic chemistry course, I'd tell you all the steps that goes through all of this stuff to form, right? And on one hand, you'd be like, God, I don't want to remember all those steps, right? And so now you're glad you don't have to remember them. But on the other hand, it would allow you more to understand what's taking place. And so, from that point of view, it'd be easier. Okay? So, you're going to have to come on and take my full-on organic chemistry class. Because I know you guys love this stuff so much. You seem so ready to take the exam right now. No? But by Wednesday you'll be ready, right? Yeah, hopefully. All right. All right, so what else can we do here? All right, let's try this. Okay, I'm going to do a sequence here. I'm going to start with this. I'm going to oxidize that. We're going to form something, and then we're going to add an alcohol to that. Oops, I wrote that wrong. With some acid. Okay, we're going to fill in these two blanks. All right, so here's a big square. We're going to put in one product there. We're going to put in the other product over here. Okay? So we already talked about this first reaction, right? If we oxidize this alcohol and we just let it oxidize as far as we can, what functional group are we going to get? Not the ketone. The what? Then aldehyde first, and what happens to the aldehyde? No. We're going to oxidize that thing as far as we can. Bingo. Right? So the alcohol gets oxidized to the aldehyde. It can oxidize again to the carboxylic acid. Right? So let's draw out the carboxylic acid. Okay, so we could say here and here. I could maybe even give you a hint, say down here, it's going to oxidize 2 times. Okay? And then we've got a carboxylic acid, and we're mixing it with methanol with some acid. Okay, so then what happens? No, not a hemiacetal. An ester. Excellent. So now we're going to form, so we have a carboxylic acid with an alcohol, we form an ester. Right, and then we give off some water. Okay? If we did this with an aldehyde or a ketone, then we can form the hemiacetal or the acetal. But when we have a carboxylic acid, then we form the ester. Okay? So let's do another reaction. So what if let's do one like this. Is that what I want to do? No, that's not what I want to do. All right, let's just start here. That won't be too fancy. Okay, so what if we add H2 and then a metal? So the metal could be something like palladium or platinum or nickel. Those 3 usually. Anybody know what happens here? What kind of reaction is this? A reduction. This is a reduction reaction. So we're going to add H's during a reduction. Remember, in oxidation, we removed H's. For reduction, we're going to add H's, right? They're just the opposite process. All right, so we're going to go backwards. We're going to add an H to each side of the double bond, and we're going to get rid of the double bond. All right, so we got this. We're going to add an H here. We're going to add an H here. Okay, so from a ketone, if we reduce a ketone, we get a secondary alcohol. Right? So this is just reverse of what we did just a few minutes ago, because if we take that secondary alcohol and we oxidize it, we get the ketone. All right? So these are really the same relationship. It's just going in one direction or the other. Okay? Okay, so we can do the same thing with aldehydes. Okay, we can.
Hydrogenation, like, is that reduction or oxidation?
That or hydrogenation, that's exactly what this is right here.
Okay.
So we're adding hydrogen, right? So it's called a hydrogenation, right? We can do hydrogenations of carbon-oxygen double bonds. We can also do, this would have been from last semester. We can also do hydrogenations in the same way for carbon-carbon double bonds. All right, and so it takes the double bond and it just saturates it. It adds more hydrogen. So remember, this would have 2 hydrogens here already, and then we're adding another one on each carbon, so each position would have 2 hydrogens. Okay, so it's the same process. We added 2 hydrogens here, we added 2 hydrogens here. They're both double bonds. One is just a carbon-carbon double bond, the other one is a carbon-oxygen double bond. All right? All right, so what if we have something like, let's see here. Something like this. Let's just put on some extra stuff just to make it look complicated. Okay? No matter what I put on here, this and this and this and this and this, and it doesn't matter, because what we want to do when we analyze this problem, we want to focus in on whatever is the functional group. Okay? All that other stuff, the alkyl part, doesn't matter. Okay? So when we look at this, we're going to focus in right here. Focus. All right? What kind of a functional group do we have? An ester. Good. So what if we treat this ester with hydroxide? Does who split up? Huh?
The skeletal structure, does it split up in ester?
We split it up into an ester?
Or does it split up
Maybe. You're really zeroing in there. You might want to you got to take one step past this before the exam, I'm thinking. Yes, so it's going to be, we're going to add, essentially going to add a water molecule, so it's going to cleave the double bond, or cleave the ester. Yes?
What kind of reaction is this?
I was just getting there. I'm going to cleave the bond with water. Cleave with water. So what should we call it? A hydrolysis. Right? Hydro for water, lysis for cleave. Okay, so this is a hydrolysis. This is a base hydrolysis. We learned, or we talked about, maybe you haven't learned yet, but we talked about how we could hydrolyze esters in 2 different ways, either in acid or in base. Okay? When we do it in acid, or in base, that's what I have here, we just draw all of the same stuff. Let's just draw everything. I got all this crazy stuff drawn on here. Doesn't matter what it is, we just redraw this part. To that point, and that's where we're going to cleave it. So let's just take out that bond. Okay? When we do it in base, what we're going to end up with is an H on this side and an O minus on this side. Okay? And if we, sometimes you'll see, and I know this is sometimes confusing, sometimes, you can't just add only hydroxide, right? You can't just add only an anion. It always has to have a cation with it, right? So you might use something like sodium hydroxide, all right? And so sodium here has a plus. It comes in just going along with the OH minus. It's just matching, balancing the charge. And so it will continue to just balance the charge in the reaction. So when we get over here, the sodium plus would just follow where the minus charge is. Okay? Doesn't really participate, it just kind of is a spectator. All right, so this is the base hydrolysis. We could also do this with an acid hydrolysis, so H plus and water. Same thing would happen, except instead of having this O minus, this is the basic form of the acid. You would get the acidic form of the acid. All right, so again, we'd cleave that same bond. Draw all this other spaghetti on here. Draw that. Okay, we can draw the other part. We've cleaved that bond. We're going to now add a water molecule in up here. And so we're going to have an OH here and an H over here. Okay, so in this case, we've really added a molecule of water. Here's our molecule of water. Up here on the upper one, since we used base, hydroxide, kind of here's our hydroxide that we added. Okay? And in the top one, even just to balance it, we added hydroxide with a minus, so we end up with the product with a minus. All right? Okay, what else do we want to do? What do you think we get if we have this plus OH minus? What functional group are we starting with? Yep, a carboxylic acid. Yep. Sometimes called a carboxyl group. And so we got a carboxylic acid. And we're adding hydroxide. What kind of a thing does hydroxide do?
It's not ready to answer that question. So is the only difference between carboxylic acid and ester that H that's attached to the O?
Yeah, so a carboxylic acid has essentially, so all of these carbonyls essentially have this part, right? And all of them that we've drawn depend on what's over here, right? So if we added an H, we got one functional group. If we added a carbon, we had another functional group. If we added an OH, we've got one functional group. If we add something like an OCH3, we have another functional group, right? So they're all depending upon what this red group is, right? So let's just remind ourselves what all of these are, right? So what's this first one over here? Aldehyde. What about this one? Ketone. This one? Carboxylic acid. And this one is an ester. Okay? So it just depends upon the combination of atoms, what functional group it is. Okay? So, what role, getting back to my question, does hydroxide typically play? What do we think about it as? A base. Exactly right. So base. What about a carboxylic acid? An acid. Hey, good. Okay, what do acids and bases do when they react with each other? They transfer protons, right? The acid gives off a proton, the base accepts the proton, right? And so in this case, the acid will give off its acidic proton. If it loses an H plus, then it ends up with a minus, right? Plus the OH picks up another H, becomes water, okay? There was a special name for this reaction. Do you guys remember? Neutralization. Okay? All right, is that enough? Okay. Kind of feels like maybe we made a little progress. Yeah, tomorrow we'll go over some carbohydrates. Okay?